Was posted. Check that as necessary. I decided on a due date for special quiz 1. The 30th of this month.
That's a Wednesday.
What? The 30th is a Wednesday? That can't be. Because I said it's Tuesday. How about that? Is that a Tuesday? Pretty bad when I can't even read a calendar. Okay. And after we have exam 2, which is next week, on the 24th, difficult location to find. And early birds will have the same location, this time with the possibility of starting at noon should you wish. Lee 309 as last time. I need a note for those of you who are in the early bird category, just so I can count noses. And after we get exam 2 evaluated, then I'll develop special quiz 2. Since I'll get ideas from the most commonly missed questions and problems on exam 2, which will provide considerations that I will make to develop special quiz 2. Now then, a couple of other announcements. Please note the syllabus tells you folks that if you have business regarding yourself in this gathering, which it requires you to get in contact with me, what are you supposed to do?
Go to your office.
See me in my office. If this thing is important to you, then see me in my office, because more often than not, considerations which are of concern to you will involve scheduling issues or inability to solve a problem. Well, I'm not going to deal with that by email. That's clumsy. If it's important, you see me in person. Now, I don't mind you sending an email saying you can't see me during office time, so when can I see you? I'll respond to something like that. But don't try to resolve this matter by email. That I won't accept. And regarding an issue which I believe I mentioned to you previously, the people who construct the operating calendar for the University of Florida are at best very stupid or negligent in their duties. Because with all the holidays we have in fall term, we have 4, I think this term, 5 fewer lectures than we do in the spring. There's no way it's possible to present the same course, to present the course as it should be presented with this shortage of lectures. There's no way. So, as we get near the end of the term, which is rapidly approaching, I will be forced to direct you to go to our video website for the class, JC Horvath, Wikispaces, whatever, if you want to use the web address, or just sit down on Google and write in Absolutely Chemistry. You'll get there. That's where all the videos for this gathering are posted, and all the videos from the last time I taught this course are posted. That would be summer. So I'll have to direct you to take a look at a couple of these videos so we can get at all the material we need to get at. Now, I don't think this is a particular burden, since you can look at these videos at your leisure pleasure. Whenever you want to, you can watch them over and over again, stop them, pause them, do whatever you want. Very simple. Just like the videos for this term. If you need a review, anything that you didn't catch during lecture, hey, look at the lecture again. It's there for your use. So when I decide on which videos you need to look at, I will of course let you know. They'll be identified by a video number and a date. Now then, back to our Chapter 19 issue regarding solubility of the specific material calcium carbonate in the presence of the specific ion ammonium ion. Given that ammonium ion is a stronger acid than water, and given that neither ammonium ion nor chloride ion bring about precipitation of calcium carbonate, we know before we do any calculation that the solubility of calcium carbonate in the ammonium chloride solution exceeds the solubility of calcium carbonate in straight water. Now, it may not exceed the solubility in straight water by a whole lot, because ammonium ion, even though it's a stronger acid than water, is still not a strong acid at all. In fact, in 46L, assignment 3, which by now I expect all of you folks are finished with, at least I hope you are if you're making progress, you were asked to investigate the solubility of calcium carbonate in ammonium chloride solution. What'd you find out? Were you able to effectively dissolve calcium carbonate by treatment with ammonium ion? In fact, a part of this investigation was, after you prepared saturated solution of calcium carbonate in ammonium chloride solution, work in lab, you were asked to carefully observe the odor of the system, because a product of this system is ammonia. And ammonia has a very strong, acrid odor. Not a pleasant odor at all. But ammonia is also quite soluble in water. So if ammonia is present in a solution, but present at small concentration, and you go and take the solution and waft the vapors toward your nostrils, you don't put your nose over the system. Ammonia is pouring out of that system, you're going to knock yourself flat. We're not trying to do that. Ammonia is present in the system, but at very small concentration, you'll just get a trace, faint odor of ammonia. You were asked to do this for this system in lab. How many of you remember doing it? Did you get any odor of ammonia? Well, I did this. Every bit of work in that lab book I've developed, or at least most of it, before I invite you to do it. I got to be sure this stuff will provide reasonable results before I invite you to do it. After all, you're here to learn. I can't expect you to be in there and be successful from a strict first principle standpoint. In other words, make researchers out of you when you first waltz in the lab. That's not fair. You haven't got the tools yet to know how to be a researcher, but you're getting them. Well, and when I did this, I did get a faint odor of ammonia. It's not much. You can get a faint odor. Well, that keeps with this equilibrium reaction. Pardon me, it keeps with the equilibrium constant for this equilibrium reaction. There's the reaction. That's how you evaluate K. K is 7.2 times 10 to the minus 8. You remember calcium carbonate plus water? Products calcium ion, bicarb ion, and hydroxide ion. K was 1.3 times 10 to the minus 12. Well, it keeps with the simple fact that calcium carbonate is very slightly soluble in water. Well, look at this K value. Is this suggesting that calcium carbonate is particularly soluble or particularly easy to dissolve by treatment with ammonium ion? Is this a big number? Hell no. So this is telling you, hey, I'm not going to effectively dissolve calcium carbonate by treatment with ammonium ion. Better than water, but still not effectively at all. Now then, regarding this system, let's ask a question that is of particular consequence. We know that the solubility of calcium carbonate will be equal to the equilibrium molarity of calcium ion. Because when calcium ion goes into solution, it doesn't engage in any further chemistry. But what about the possibility of the solubility of calcium carbonate being equal to, or more or less equal, close to, the equilibrium molarity of bicarb ion as well as the equilibrium molarity of ammonia? Let's pursue that issue. Clearly, the strongest acid in the system is ammonium ion, and the strongest base in the system is carbonate ion from calcium carbonate. So we look at this reaction, just to get a handle on the extent of the acid-base reaction between ammonium ion and carbonate ion. You know how to calculate K. But even without K calculation, you can recognize this is a large extent reaction. You get out the acid-base table, you see Ka for this is 5.6 times 10 to the minus 10, and Ka for this, the product acid, is 4.8 times 10 to the minus 11. So Ka this is over 10 times bigger than Ka this. So you know this is a large extent reaction. Point: ammonium ion effectively converts carbonate ion to the products bicarb and ammonia. So if you take a system that's rich in carbonate ion, I mean a solution that's rich in carbonate ion, not a solid, because in order to get that to go in the solution, you got to kill the lattice as well. It isn't just acid-base chemistry. It's lattice stability also you're fighting. But if you take sodium carbonate solution, say 10th molar, a solution rich in carbonate ion, and treat that with ammonium ion, if you take a healthy whiff of that system, it's going to knock you flat. Because ammonia gas is going to percolate readily from that system. But what about the possibility of ammonium ion and hitting bicarb ion to make H2CO3 and ammonia? What do you say about the extent of this reaction? Well, Ka this, 5.6 times 10 to the minus 10. Ka this, the product acid, 4.2 times 10 to the minus 7. So now we recognize the product acid is a good deal stronger than the reacting acid. So based on what we have considered in chapter 18, we will assess the extent of this reaction to be small. But is it possible to make this reaction go, perhaps not to a large extent, but to an extent that's large enough that we have to consider in analyzing the system thoroughly? Is it possible? By what method is it possible? The method to which I refer is vernacularly referred to by me in the notes as the gang-up factor. You remember the gang-up factor? I don't know if I told you this story yet. Maybe I did. Any of you familiar with a guy whose name is Muhammad Ali? I'm not much for pugilism. Well, that guy was nice to watch. Float like a butterfly. Indeed he did. Sting like a bee. When that guy was in his prime, he may well have been the best heavyweight that ever stepped into the prize ring. What would happen if, when Muhammad Ali was in his prime, any one of us would have put on boxing gloves and jumped in the ring with him? Kapow, and away we go. But if the whole damn bunch of us jump in there, maybe 40 or 60 or 80 of us would get killed along the way, but eventually we'd overpower them by the gang-up factor. Do we have a gang-up factor operating on bicarb ion in this system? Because this K value tells us, A, we do not effectively dissolve calcium carbonate by this method. But B, the ammonium ion molarity is 1 molar. So do you think in this system, the ratio of ammonium ions to bicarb ions is hugely in favor of ammonium ion? Absolutely. So by the gang-up factor, we may well, convert some of this, at least measurably, to this. Now, if this is true, then this will not be true. But we want to see if what we've said here is true. I mean, if nothing else, we've already recognized ammonium ion plus carbonate ion is a large extent reaction. We already know that calcium carbonate in straight water hydrolyzes, carbonate ion hydrolyzes about 70%. And given that ammonium ion is a stronger acid, good deal stronger acid than water, the hydrolysis or conversion extent of carbonate ion to bicarb ion is going to far exceed 70%. And if it's true that ammonium ion plus bicarb ion doesn't go to a particularly significant extent, then the principal carbonate-containing species in this system by far is bicarb ion, just like it was at pH 8. I'm just discussing the considerations which support this approximation. Now let's pursue this approximation. Well, if it's true that the calcium ion molarity, the bicarb molarity, and ammonia molarity are all about the same, because again, calcium ion certainly is S, and we're speculating that bicarb molarity and ammonia molarity are also about the same, then the K algebraically becomes this. And if I solve it for S, I get 4.2 times 10 to the minus 3 molar. So if this is true, and I compare it to 1.4 times 10 to the minus 4 molar, which is the solubility of calcium carbonate in deionized water, this keeps, because this is a lot bigger than this, because we already know whatever the solubility is of calcium carbonate in the ammonium chloride system, it's got to be bigger than the solubility in straight water. This number is also bigger than 1.1 times 10 to the minus 3. Remember where we got this number? That was our calculated calcium carbonate, our calculated calcium carbonate solubility in water solution buffered at pH 8. This number is bigger than that. So again, if this is true, what can we say about the pH of our ammonium chloride solution saturated with calcium carbonate compared to this? Is the pH of the ammonium chloride solution saturated with calcium carbonate guaranteed to be smaller than this if this is true? The more acidic we make the system, the more soluble we make calcium carbonate, because the more acidic we make the system, the more effectively we murder carbonate ion. We've been through this. So by what we have done, we have got a solubility value for calcium carbonate in the ammonium chloride solution, which exceeds the solubility of calcium carbonate, which we calculated at pH 8. So this is screaming at us. The pH of the ammonium chloride solution saturated with calcium carbonate has got to compare how to 8? Got to be smaller. Got to be more acidic system. Now then, what about pH 6? Because we did that calcium carbonate solubility calculation as well, and we got 2.1 times 10 to the minus 2. Well, this number is bigger than this number. So now we get another handle on system pH, this system. Given that this solubility is bigger than this solubility, now we've got information which strongly supports the conclusion that the pH of the ammonium chloride solution saturated with calcium carbonate compares how to pH 6? Bigger. Hey, we're just taking advantage of stuff we already know. So this is telling us, if what we've done here is reasonable, the pH for the calcium carbonate ammonium chloride solution system is in here someplace, right? Letting this stuff talk to us. That's what you got to do. And that's the hard part. That's the part of the puzzle with which I am very sympathetic for you folks. Because this is the hard part. Learning how to examine this stuff like a research chemist. But that's what chemistry is all about. If you want to ever understand the stuff, that's where it's at. The stuff that textbooks give you, where they give you a recipe and shove data into the recipe and push buttons on the calculator and get an answer, and then pat yourself on the back. That's baloney. Because it doesn't involve any thinking. It involves grinding like a monkey. Monkey see, that's the stuff they showed you. Monkey do. Monkey get answer, monkey make A. A mean nothing. This 2045. I'm trying to make those people understand that's not the way to run the course. You've heard that before, haven't you? Think you'll hear it again? Hell yes. Now then, from what we have done here, how could we calculate pH? Hey, let's pick on this, which is the principal acid in the system, for which Ka is this. There's the Ka chemical expression for ammonium ion, and recognize that based on the work we have so far done, we know the ammonium ion concentration at equilibrium, we know the ammonia concentration at equilibrium. The ammonium ion concentration will be 1.0 less this number, right? Material balance applied to? Because we know this. Mb 1.0 equals this. Plus this. Mb for ammonia, ammonium ion. Well then. But I think at a glance you can see that 1.0 less this number, from a significant figure standpoint, doesn't make 1.0 get smaller. But you have to cheat on significant figures with this stuff till you get to the end of the line and then pay attention to significant figure limitation. So I take this to 3 sig figs at least, read this as 4.20, and then subtract that, and I will reduce 1.0 to a somewhat smaller number, put that in there, and that's going to give me a hydronium ion concentration that's really a little bit smaller than this. You can do that. You know what I'm talking about. Write 1.00, subtract from it this number. Or 1.000 and subtract from it this number. And put that in for a better estimation of the, of the ammonium ion molarity. Because I took this and rearranged it to get this. Hydronium ion, here's Ka, ammonium ion up here, ammonia down here. Okay? So here's the ammonia molarity. This should be really 1.000 less 0.0042. Then do the arithmetic. So you get a hydronium ion molarity that's a little bit smaller, 1.3 times 10 to minus 7, which means we'll get a pH that's a little bit bigger than 6.89. Call it about 6.9. And now comes the bottom line, if you will, on this system. Is what we did here reliable? Is it accurate? How can we find out? 2 ways to find out. I wrote this here. How can we check the reliability of what we did? We'll do the calculation rigorously. That's already been done. We'll talk a little bit more about that in a moment. My reference to you is Bonus Quiz 2, Summer 2011. It's all available for you on the Sakai resource. Or, what I'm trying to achieve is to get a good pH meter. Standardize it properly. Prepare the system. Take 1.0 molar ammonium chloride solution, make it carefully, and saturate it with calcium carbonate. And measure the pH. And see what we get. If we were to get 6.9, hey, this thing is right on the nose. But I know we're not going to get 6.9. We'll get a number close to 6.9. But the number we will get will be closer to 7.0 than it is to 6.9. Number one, because we've already recognized that the ammonium ion molarity is a little bit smaller than 1.0. Number two, because the gang-up factor drives this a little bit to the right, what does that do to the ammonia molarity if this goes measurably? Does that make the ammonium molarity get bigger than what we have decided here? Does that make the ammonium ion concentration get smaller than what we decided here? Yes and yes, because this makes ammonia while consuming ammonium ion. So I got another reason to recognize why the true ammonium ion molarity is less than 1.0 and the true ammonia molarity is bigger than 4.2 times 10 to the minus 3. Number 3. Ha-ha! Come on, chemists. Is there another reaction involving ammonium ion in this system, which, because of the concentrations that we encounter in this system, we also have to consider? Is there another reaction in this system which would result in upping the ammonia molarity while lowering the ammonium ion molarity? What is this other reaction? Well, say it louder.
Reaction with water.
Of course. So we'll add another thing under our considerations. What we're now doing is paying attention to all the chemistry that's occurring in this system, which has a bearing on our concern, the solubility of calcium carbonate. There's no question about this equilibrium being fine. But what's at issue here is, what is the true equilibrium molarity of ammonium ion? What's the true equilibrium molarity of ammonia? And when we look in a very careful fashion, which is what we've just done, we have come to recognize that the true ammonium ion molarity is certainly smaller than 1.0. Not a whole lot smaller, but smaller. And the true ammonia molarity is certainly bigger than 4.2 times 10 to the minus 3. So by calculation, how can we do this rigorously? What else do we have to pay attention to beside this equilibrium reaction? I'm listening. I'm listening. I heard it. Louder. Yes. We've given you these tools. So now it's your job to put them to use. So in addition to this equilibrium reaction, for which we've already evaluated K, in addition to this material balance consideration, because this sums up the molarities of all the possible material forms of carbonate-containing stuffs. Now for this expression, which of these terms do you think, practically speaking, we can neglect? Which one? Which one? Carbonate ion. You remember at pH 8? At pH 8, the bicarb molarity was 210 times bigger than the carbonate molarity, whereas at pH 8, the bicarb molarity was 42 times bigger than H2CO3. Well, when we got to pH 6, the predominant form of carbonate in the system was H2CO3. But at pH 6, the bicarb molarity is 21,000 times bigger than the carbonate molarity. And we've already determined that the pH for this system is in here someplace. It's more acidic than pH 8. So, practically you can forget this stuff. But not this, if you want to do the calculation in detail. Now then, just to get you started, you can work on this on your own. It's something that I would never ask you about to do the calculation on an exam or quiz because it's too time consuming. But something I gladly ask on quizzes, take-home quizzes, which is what the special quiz or the bonus quiz is. And again, you can look at the thing in detail. because it's there available for you. But you're going to need charge balance. So let's write the charge balance for this system. Positive ions first. Being sure to keep hydronium ion in this charge balance, because that's really what we're trying to get a handle on, is this hydronium ion molarity. Because when we get the hydronium ion molarity, we'll know about the true equilibrium molarity of ammonium ion, and the true equilibrium molarity of ammonia, and the true solubility of calcium carbonate. Negative ions. This, but this is not adding another unknown, because that's equal to this. This, if we want to be completely rigorous, we'll put this in, but we've already recognized that this can probably be struck from this computation. Anything else? Don't forget chloride. Especially don't forget chloride, because we know what the molarity of this is, don't we? What is it? 1.0. So there's your charge balance equation. And now you have enough equations to solve the puzzle. You do the work. It's good practice for you. You will get that's right. Thorough analysis. Gives S equals calcium ion molarity. It's 4.4 times 10 to minus 3. Hydronium ion molarity, 1.2 times 10 to minus 7. That's pretty close what we got here. pH 6.92. Bicarb molarity 3.4 times 10 to minus 3. And so that's telling us, yeah, this has gone. The bicarb molarity is not the same as S, it's a little bit smaller than S. And given that we've recognized that the other carbonate containing thing in the system that we have to pay attention to is quote unquote H2CO3, we'll note its molarity. (9.7 times 10 to minus 4). So hey, this is gone. Not to a large extent, but it's gone to a large enough extent that we have to pay attention to it. Do the arithmetic. Good practice. And in the main, why did I do this? I did this to show you what we told you about a few lectures back, where we reminded you that after we go through the equilibrium considerations for acid-base chemistry that we looked at in detail in chapter 18, and support that with material balance considerations and charge balance considerations. You can take apart any water solution system that you want, like this one, and calculate correctly the concentrations of everything in the system whose existence depends on pH. This is an example of such, no more, no less. Pretty powerful tool, especially if you're going to do something with things like biochemistry. Important. You think the chemistry of living systems is important? I'd say it's a hell of a lot more important, at least now, compared to what is the composition of rocks on Mars. Is that important too? Yeah! But is that as important as this? No! That's my opinion. So we proceed. There are two remaining issues with which we want to deal in Chapter 19. They are taking a look at a semi-soluble salt equilibrium. Just to be sure we know or are familiar with the various ways by which the equilibrium condition can be affected. The various physical and chemical methods by which an equilibrium system can be affected. So we're going to pick on this equilibrium system. You'll see this considered in detail in the notes. Starting on page 1916. Okay? So I would like you to look at this carefully before our next meeting. And in addition to this, one more consideration. Section 19.4 in the notes. Altering S for a semi-soluble salt by complex ion formation. Remember when we talked to you about learning how to calculate K for an equilibrium system for which the K value is not supplied? So you got to figure out what are the fundamental Ks of which this K is composed. And at the time at which we introduced you to this, we had before us Ka, Kb, Kw, and in chapter 19 we learned about KSP. So we learned about one more K. K sub F, where the sub F means formation. Formation of a complex ion. So I'll write here for altering S by complex ion formation, consider this. Any of you folks as yet in lab approaching assignment 6? You folks who are in assignment 6, have you done this? In assignment 6 in lab, as a look to the future for your lab work, you'll precipitate silver chloride. Nothing fancy about that. You already did that in assignment 2, for example. Okay? You may have done that in high school, I don't know. And then you're going to treat the silver chloride with ammonia solution. And voila, you'll find out that the silver chloride can be dissolved by attack with ammonia. How about that? In this case, the silver chloride is dissolved as a consequence of complexing silver ion to make this complex ion, the silver ammonia complex ion. Not surprising that that's what its name is, since it's composed of silver ion and ammonia molecules. As chloride ion goes into solution. Okay? So on Monday, and as necessary on Wednesday, because our intention for exam number 2 is to finish chapter 19. We'll be looking at this. So I'm telling you to read this stuff and have a handle on it before we discuss it in class.